Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Okay, let's unpack this. Look up at the panel of any aircraft, from a tiny little trainer to a huge airliner, and you're going to see it. That small, kind of unassuming instrument, the magnetic compass. It looks, frankly, archaic next to all the modern glass screens, but it is the ultimate universally mandatory backup, and I mean mandatory. It's required by Title 14 of the Code of Federal Regulations, Part 91. Every single flight, VFR, IFR, if all your fancy electronics go dark, this little floating card is what points you home. But, and this is especially for you student pilots out there, you learn fast that its simplicity is, well, it's a mirage. So this deep dive is all about the core physics and, the frustrating little quirks of your final directional safety net.
And it all starts with just pure, magnificent physics. The only reason this thing works is because our planet, the Earth, is a gigantic spinning magnet. It's constantly generating these invisible lines of flux. They leave the planet at the magnetic North Pole, they curve all the way around, and then re-enter at the magnetic South Pole. So the compass is just a clever little device to harness that. You take a small magnet, you let it float freely, and it will always try to align itself with those lines, and boom, you have a heading.
So let's get into the nitty-gritty. How do you make that tiny magnet actually useful in the turbulent, vibrating world of a cockpit? What are we looking at inside that little instrument?
We're looking at a system that's all about delicate balance. You have two small magnets, and they're attached to a metal float. The whole assembly is sealed up in a non-magnetic case filled with this clear compass fluid, which is usually something like a purified kerosene.
And that fluid is doing some really clever work. It has two jobs, right?
Exactly. First, it provides buoyancy for the whole magnet and card assembly. This is critical. It takes almost all the weight off the pivot point. That whole thing rides on a tiny, hardened steel pivot sitting in a little spring-loaded jewel cup, often sapphire. If it had to carry its full weight, friction would just make it useless.
And the second job is damping. In turbulence, that card would want to swing all over the place, right? Oscillating like crazy.
Wildly. So the fluid provides resistance. It damps out those oscillations and actually makes the instrument readable.
Right.
And speaking of that fluid, temperatures change, so the liquid expands and contracts. To handle that, the compass housing has a flexible diaphragm, or sometimes a little metal bellows, in the back. It's basically a tiny expansion tank that manages the pressure so it doesn't leak or break.
Okay, so let's talk about the display itself. The graduated scale, the card wrapped around the float, it's got the cardinal directions, and a numbering system where the last zero is always missing. So 3 is 30 degrees, 21 is 210.
And you've got your long tick marks for 10 degrees and the short ones for 5.
So for all you student pilots, here is where it gets weird. The confusion factor. We've all been there. You're flying north, you look at the compass, and the number for 330 degrees, which is west, is on your right. It feels totally backwards. Why?
It's so counterintuitive. And it's because of how the display works mechanically. You see, unlike a directional gyro, the magnetic compass card itself stays pretty much fixed. It's aligned with the magnetic field. You are the one viewing the card from its backside.
Right. So when you turn the airplane, the compass housing, and us, the pilots, we're rotating around the stationary card.
Exactly. So if you turn right, the card seems to swing left across the top to show you the new heading. It's a reference system that just takes some practice to get your head around.
And that brings us to maybe the biggest mechanical limitation, the one you have to memorize. The bank angle limit. Because of that delicate jewel and pivot mounting, the float can only tilt up to about, an 18-degree angle of bank.
That's it. About 18 degrees. You go past that, and the indication becomes erratic, unpredictable, frankly useless. It's a straight and level instrument. If you're in a steep turn, you have to rely on your gyro. You just ignore the magnetic compass until you level out again. That is a critical constraint.
Okay, so once we master the weird way it reads, the next challenge is dealing with all the errors. The Earth's own magnetic field isn't perfect, and neither is the airplane. So now we need to talk about the two main fixed errors, the ones you need to convert your true course to the compass course you actually fly.
And we start with variation. This is purely a geographic problem. See, when you plot a course on a map, you're using true directions, which are based on the geographic North Pole. But your compass, it points to the magnetic North Pole. And that magnetic pole is always shifting. Right now it's about, 1,300 miles away from the true pole.
So variation is just the angle between those 2 points.
Exactly. And the key thing to remember is that variation only depends on your location. It has nothing to do with which way the plane is pointing. If you look on your aeronautical charts, you'll see these lines connecting points of equal variation. Those are called isogonic lines.
And there's the famous one, the agonic line, right? Runs sort of through the middle of the U.S., near Chicago. That's where variation is 0.
Correct. Along that line, true north and magnetic north are one and the same.
Let's do a quick example because this is where it really matters for you, the pilot.
Yeah.
Say we're flying near Washington, D.C. The variation there is about 10 degrees west. So if your true course on the map is 180 degrees, you have to add that west variation. Your magnetic course becomes 190 degrees.
But now let's take that same 180-degree true course and fly it out of Los Angeles. Out there, the variation is about 14 degrees east. In that case, we subtract the east variation, so your magnetic course would be 166 degrees. It's all about remembering. True course plus or minus variation gives you magnetic course.
Okay, so we've got our magnetic course, but we're not done yet. Now we have to deal with deviation. But wait, why do we fix variation first? Wouldn't the airplane's own magnetism be the more immediate thing to worry about?
That's a really good question. We do variation first because it's the global constant for your location. It defines the magnetic environment you're in. Deviation is the internal interference. It's the aircraft's electrical currents, its radios, maybe some magnetized metal parts, all messing with that local magnetic field. So it's more logical to find the pure magnetic direction first, then see how your specific airplane is distorting it.
And unlike variation, deviation changes completely with your heading, right?
Completely. Turn the plane 90 degrees, and the magnetic influence of the engine block or the radios changes relative to the Earth's field, so the error changes too.
So how do we fix it? Or at least account for it?
Well, we can minimize it. This is a job for an aviation maintenance technician, an AMT. They do a process called swinging the compass.
Right, I've seen this on the airfield. They put the plane on a cleaned compass rose on the ground, somewhere with no metal interference, and they line it up on the cardinal headings: north, east, south, west. Then they use a special non-magnetic screwdriver to turn these tiny little compensating magnets inside the compass itself.
Exactly. Those little magnets are there to counteract the worst of the aircraft's own magnetic fields. But you can never get rid of the error entirely. So the AMT records any small leftover errors for every 30-degree heading.
And that becomes the compass correction card. That little card taped right next to the instrument. And as the pilot, it's your job to use that card to find your final compass course. And you have to remember, if you turn on pitot heat or a certain radio, that can change the deviation.
So let's put it all together. You start with true course from your map. You add or subtract variation to get magnetic course. Then you look at your correction card for that magnetic heading, and you add or subtract the deviation. That gives you your final compass course. So in our DC example, if we had 190 degrees magnetic, and the card says for a 190 heading, you subtract 2 degrees of deviation, you steer 188. That is the number you fly.
Okay, now for the part that gives every student pilot nightmares. The dynamic errors. These are the errors that only pop up when the compass is tilted or moving, and they all come from one single concept: magnetic dip.
Yes, you have to internalize magnetic dip. Remember those lines of flux? They only run parallel to the ground at the magnetic equator. As you get closer to the poles, those lines start to pull vertically. They dip down towards the Earth. So that force is trying to pull your little compass magnet straight down.
And the engineers tried to fix this by lowering the center of gravity of the float to keep it horizontal. So in straight and level flight, it's mostly okay. But the second you bank the airplane, or change your speed, that pendulous mounting lets the vertical part of the magnetic field create all sorts of misleading forces.
And that force is what causes the northerly turning error. We call it lead. So imagine you're on a northerly heading and you start a turn. Because you're banked, that dip force pulls down on the compass card,
Which causes the float to swing, or lead, in the direction you're turning. So the compass shows you're turning faster or are further along in the turn than you actually are.
Exactly, a false northerly indication. And because of that lead, you, the pilot, have to stop the turn before you get to your desired heading. And this is where that famous latitude correction rule comes in.
The rule every student has to memorize for the test: stop 15 degrees plus half of your latitude early. Let's make that real. If you're flying in a northern state, maybe at 40 degrees latitude.
Okay, so half of 40 is 20. Add 15, that's 35 degrees.
So you have to roll out of your turn when the compass says 035 just to end up on a heading of 360, or north. That is a massive correction.
It's huge. And now for the opposite, the southerly turning error, or lag. When you turn toward a southerly heading, the forces combine to make the compass lag behind the turn. It shows you not as far along as you really are, a false southerly indication.
So for a southerly turn, you have to let the compass card go past your desired heading before you stop the turn. If you're near 30 degrees latitude, that would be 15 plus half of 30. So 15 plus 15. You'd stop 30 degrees after passing your heading. It just proves how tricky this thing is when you're maneuvering.
And finally, there's acceleration error. This one only happens when you accelerate or decelerate on a pure easterly or westerly heading. It's all because of inertia acting on that pendulous mounting.
Explain the why of that one, because on the surface, it feels totally random. Why would changing speed affect your direction?
It's because the float assembly has mass, and like we said, it's mounted like a pendulum. When you accelerate, inertia makes the assembly swing backwards. This tilts the back end of the card up. That tilted magnet then reacts to the vertical dip field, and it causes a false turn toward north. Decelerate, and it swings forward, tilting down, which indicates a turn towards south.
And that explains the mnemonic that every PPL student needs tattooed on their brain. ANDS, acceleration north, deceleration south. Only works on east and west headings, but absolutely critical to remember when you're taking off or landing and trying to align with the runway. So you can find all these errors fixed and dynamic, and you get our next one, oscillation, which is just the simple swinging back and forth of the car.
Precisely. You see it in turbulence, or right after you stop a turn. The key practical tip here is when you're setting your directional gyro from your magnetic compass, which you should do every 15 minutes or so, don't just pick one end of the swing. Use the average indication between the swings. That's your most accurate heading.
You know, with all this complexity, the reverse reading, the deviation card, latitude rules, ANDS, it's not a surprise that engineers looked for a better way. And that led to the vertical card magnetic compass, or VCMC.
Yeah, the VCMC was made specifically to get rid of that reading confusion. Instead of looking at the back of a horizontal card, it uses a vertical rotating dial. It's actuated by gears, and you read your heading against a little symbolic airplane. It looks and feels much more like a regular directional gyro.
And they improved the damping, too.
A lot. It uses what's called eddy current damping. Basically, the magnetic flux from the swinging magnet creates tiny electrical currents, and those currents create their own magnetic field that opposes the swing. It smooths it out almost instantly.
A huge improvement.
But there's a catch, isn't there?
There is. A very specific one for pilots using a VCMC. Its dynamic turning errors are different. They're actually reversed.
When you start a turn from a northerly heading, the vertical card lags behind the turn, the opposite of a standard compass. And when you start a turn from a southerly heading, it leads the turn. So if your plane has a VCMC, you have to know that the turning error rules you learned are essentially flipped on their head. Hashtag tag 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 outro, Soma.
So what's the takeaway here? The magnetic compass, it's the one instrument you can always count on, but it demands some serious respect for its limitations. For you preparing for your PPL, internalizing ANDS, understanding the strict correction sequence of variation, then deviation, and applying those latitude rules for turns. That's what separates a good pilot from a great one. It's like an honest friend, you know?
Yeah.
It's reliable, but only if you really understand its quirks.
And if we connect this to the bigger picture, it's just amazing to think about the engineering that went into making a three-dimensional magnetic field work on a two-dimensional display. We know the constraints. It's unstable past 18 degrees of bank. It's unreliable when you're changing speed. This all leads to an interesting question. Considering how hard this device works to fight the vertical component of the Earth's field, and knowing that the magnetic North Pole is, well, it's constantly moving, and actually accelerating its shift across the Arctic, you have to wonder, how might this changing geography eventually force a complete redesign of the instrument, especially if flight paths start taking us into higher and higher magnetic latitudes, where that dip error could become just overwhelming. Something for you to mull over next time you're up there.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.